Greetings and welcome to the Chemistry 221 Exam 2 review. Exam 2 is coming up. It will cover chapters 3, 4, and 5, and this time will hopefully help you get better prepared. In the normal face-to-face version of this class, I would offer these slides coming up here, and they're basically little problems with 5 possible answers. They are all definitely exam grade questions, and I talk about the question a little bit, and then I would give the students a time to work on the problem and see how they did, and then after a few minutes I would then talk about how to actually do the problem. You can kind of see how you did, and hopefully it helps to prepare you. You can tell what you know and maybe the things that you need to work on some more. Now in this video version, what's going to happen is I'm going to show the same questions. I'll talk about them a little bit, and then I'll say, hey, this is a good time to pause the video, and I do encourage you to pause it. You can then work on the question yourself, and when you're ready you can unpause the video and then see how you did. So it's kind of the equivalent way of doing it when you're not in a face-to-face environment. So cool, I'm glad to have you here, definitely. Midterm 2 will cover chapters 3, 4, and 5, which is basically problem sets 4 and 5 of Chem 221. The exam itself will have 20 multiple choice questions, and there will be 3 to 4 short answer questions. Kind of depends on the material how many short answer questions there are. Multiple choice questions are either right or wrong, all right, and that's kind of how that goes. But the short answer questions, you can definitely get partial credit, and I want to see your work, how you set the problem up. You can get a short answer question numerically right, but if you don't show how your work is set up, then you won't get all the points. On the other hand, if you show even some of your work and it looks somewhat reasonable and your final answer is wrong, you'll still get a lot of partial credit. So on the short answer questions, definitely show me what you're doing, what you're thinking, how you would solve it and stuff like that, and you might get more credit. Now, for the online classes, the exams will be due Friday at 9 a.m. via email. If you have specific questions as to when it's due, etc., please reach out to me via email, and I can help you out more that way. But for right now, at least, it's going to be Friday at 9 a.m. And it'll take me a day or two to grade the exams, and then I'll return it to you. And when you get your exam back, look at the very last page, because the very last page is a summary sheet that's just saying like how you're doing in the class as of this time. And I encourage you to check that page out, because I want you to see, first of all, that the grades I've entered are actually the grades you've got, and I do make mistakes on that sometimes, which I apologize. They're not too many, but it has happened, so please double check. Also, if you're missing a lab or an assignment, it'll state on there that you're missing it, and it's really cool to try and get those in. The lab completion bonus is a big part of your grades, so try and get those in. And definitely, I'm wishing you the best with your studying. I hope that this time will help, and I think at this point we might as well start the review, so let's do it. This question is a question on balancing reactions, all right? And you can see up there's a reaction between H2S and SO2 to make sulfur by itself. That's elemental sulfur plus water. And it says, what statement regarding this reaction is true? And there are 5 possible answers there. In this question, you will definitely want to balance the chemical reaction to answer it. So do that part first, and then see if you can interpret that to get into the right answer. So this would be a good place to pause the recording, and when you're ready, unpause it, and we'll talk about the answer. So pause your recording now. Okay, I think, assuming at this point that you have tried the problem yourself, and let's check this out. So when you're doing this problem, all right, you can see you've got a lot of pieces up there to balance. Sulfur is by itself, all right? And sulfur would be the last thing I would want to balance, because you can see like sulfur is in both of the reactants, the H2S and the SO2. So for this one, when I look at this with my eye, I see, aha, SO2 has 2 oxygens, and oxygen is only in water. water. So I would start by putting a big 2 right there, because that will make the oxygens balance. So oxygen is down. Now I'm going to work on hydrogen. And you can see by putting the big 2 there to balance the oxygen, we now have 4 hydrogens. On the reactant side, hydrogens come in 2 in H2S, so let's put a 2 right there. And then, if all is said and done, I've got 2 sulfurs on H2S and 1 sulfur on SO2, so 3 sulfurs total. I believe that's going to be 3. Now, if you're ever uncertain as to how this all works out, I highly recommend that you balance the reaction. So let's balance this real fast. I'm going to put down the hydrogen, that's a H right there, sulfur and oxygen. And the left and right sides represent the reactant and product side. So on the reactant side, with my big 2 by H2S, I would have 2 times 2, 4 hydrogens, and 2 times 1, 2 sulfurs in the H2S. And in SO2, the other reactant, I have 1 more sulfur. Notice I had +1 right there. All right, just makes it easier for me. And SO2 has 2 oxygens. So on the right side, the product side, if we've done this right, everything will be balanced. So 3 sulfurs would be a 3 right there. 2 times 2 for water would be the number of hydrogens, or 4, and 2 times 1, 2 oxygens. And if you look, the numbers on the left, that's a pretty sloppy 4, sorry, the numbers on the left equal the numbers on the right, so this looks like it's balanced to me. So let's check or actually, before we do that, let's assume that this is the balanced reaction. We can then go through and see which one of these statements are correct. So the first one says that 3 moles of sulfur are produced per mole of H2S. Well, I like the 3 part because we have a 3 right there. However, 3 moles per mole of H2S would not be correct. There's a 2 in front of the H2S, so it would be 3 moles of sulfur per 2 moles H2S. Answer A does not look right. Then it says 1 mole of SO2 is consumed per mole of H2S. Well, there's a 1 in front of the H2S. There's like an invisible 1 right there, and you shouldn't write that, but I'll write it here as for instruction. There's a 1:2 ratio of SO2 to H2S. It is not 1:1. Answer B doesn't look right. Then it says that a mole of water is produced per mole of H2S. Now, initially, that looks like, from the balanced reaction, like it would be 2 waters for every 2 H2S, all right? But if you reduce that down to common denominator, i.e. divide both of the 2's by 2, you're going to see that that one is right. 1 mole of water is produced per mole of H2S. So 2 moles of H2S could create 2 moles of water, and 3 moles of H2S would record 3 moles of water, etc., etc. But before we do that, let's look at the other ones here. D, the total number of moles of products is always equal to the total moles of reactants. That is not the case. All right, you can see from this reaction, which is balanced, that we don't have that. There's a 2 and a 1 on the reactant side, so that would be 3 moles of reactants. And on the product side, there's a 3 and a 2, 5 moles of products. So 3 moles of products obviously is not 5 moles of products. The moles of atoms will be the same, but the moles, the stoichiometries on the reactant side are not equal to the stoichiometries on the product side. So answer D is not right. Answer E is not right. If C is right, I think answer C is going to be right, and it is. All right. So when you balance this reaction out, 2H2S plus 1 invisible 1, SO2 makes 3S plus 2 waters, and the relationship between H2S and H2O is 2:2 or 1:1. Good to go. What's the balanced equation for the combustion of butane, C4H10? So this is another example of balancing equations. One of those there is correct. See if you can work on it, and we'll go from there. So this would be a good place to pause the recording, work on the problem, and then when you're ready, unpause it. So pause your recording now. Okay, at this point, I'm going to assume that you have done this problem, and we'll check it out. A combustion reaction always has something organic, which in this case is this butane. Organic means carbon and hydrogen usually, sometimes carbon, hydrogen, and oxygen, something like that. And it will react with oxygen, O2, to make CO2 and water. So A is not correct, but it does show the raw ingredients. Something organic, C4H10 plus O2, CO2 and water are your only products. So at this point, what you want to do is you want to start balancing out different things. And like on the last example, I would balance the oxygen last, okay? And that's pretty important. Initially, C4H10, C4, I would put 4 CO2s because 4 C's on the left would balance 4 C's on the right. Water comes in pairs of 2s, so because there are 10 hydrogens in C4H10, I would initially put a 5 in front of the water. And having the 4 and the 5 there would balance the carbon and the hydrogen. But oxygen comes in 2s. It's one of the diatomics. Have no fear of ice clear brew. So on the product side right now, I would have 4 times 2, 8 oxygens from CO2 plus 5 oxygens from the water. That's 13 O's. And for O2, because it comes in pairs, I can't really have an odd number. What I'd like to do is have 13 halves O2, because 13 halves times the 2 of O2 would give me 13 oxygen atoms, which is what I want. However, you don't do that in chemistry. Chemists really hate fractions generally if you can avoid them. So instead of 13 halves, what we can do is multiply this whole thing through by 2. And if you do that, you get 2 C4H10s, and 13 halves times 2 would be 13 O2s. Multiply the other side by 2 as well, so 4 times 2, 8, 5 times 2, 10. Pretty sure answer B is right. Sure enough, it is. So that's what you'd want to do for this kind of thing. Try not to use fractions in your balanced chemical equations. It's bad form usually. And a combustion reaction is something organic plus O2 making CO2 and water, etc., etc. Good to go. In this reaction, we're putting 2 moles of CCl4 with an excess of HF, and 1.7 moles of CCl2F2 is obtained. And here's the reaction. So we have an excess of HF, which means we don't have to worry per se about limiting reactants. You want to base your calculations on the CCl4 and the 2 moles of CCl4. And then it says that 1.7 moles of CCl2F2 are obtained. And then it says which statement here is true. And you can go through those and pick the one that's correct. The last one, infinite diversity and infinite combinations, is a really cheesy reference to the original Star Trek. Long story, but anyway, I'm really into Star Trek. I couldn't resist. I'll also let you know that's not the answer. Darn it! See if you can figure out which of the answers, A through D, is correct. This would be a good place to pause the video, work on it, and then when you're ready, unpause it. So pause your video now. Okay, at this point, I'm going to assume that you've done the problem and you want to talk about the answer, which is awesome. So this is showing the power of a chemical reaction and how chemists can use a chemical reaction to predict products and all kinds of interesting things. Now, let's go through these and see what's going on. First of all, unfortunately, answer E, my beloved Star Trek, is not the right answer here, so let's take that one out. All right, so first one, theoretical yield for CCl2F2, 1.7 moles. Now, to figure out what the theoretical yield is, all right, we really should start with reactants. And as we talked about, 2 moles of CCl4 is the important part. You can see that a lot of stuff is focusing around the CCl2F2. And honestly, in this problem, no one really cares about HCl, so just ignore that one, okay? Now, 2 moles of CCl4. Every 1 mole CCl4 creates 1 mole CCl2F2. So 2 times 1 over 1, the theoretical yield of CCl2F2 is certainly not 1.7, it's 2. All right, and you can write that out formally. 2 moles CCl4 times 1 mole CCl4 per 1 mole CCl2F2, you can see that this is going to come out to be 2 moles CCl2F2. And this number, all right, which I use the stoichiometric factor 1:1, that's the theoretical yield. The theoretical yield is 2 moles. It is not 1.7 moles. 1.7 moles is the actual yield of the product, all right? Actual yields kind of have to be given to you, and that's what the 1.7 moles of CCl2F2 is. It is not 1 mole, so B is also incorrect. C, percent yield for the reaction is 85%. Well, let's figure it out, all right? Theoretical yield, percent yield is equal to the actual yield divided by the theoretical yield times 100%. It's kind of sloppy, my apologies. So in this case, we saw that the 1.7 moles is the actual yield. 2 moles is the theoretical yield times 100%. And in my calculator here, I'm going to enter that in real fast. I get 0.85 times 100%. I'm getting a theoretical yield of 85%. So I believe answer C is correct. But let's look at D first and stuff. It says the theoretical yield cannot be determined unless the exact amount of HF used is known. That's incorrect. If it says that HF is an excess, that means we don't have to worry about it. CCl4 is like a limiting reactant, so it's really going to determine what all the different pieces are. So I'm pretty sure the answer here is going to be C, and it is. And you can see down here what I did is I first calculated the theoretical yield. This is a little bit fancier than my cheesy pen scratching up there. 2 moles times the ratio of 1/1 tells you the theoretical yield, and then percent yield, actual divided by theoretical, 1.7 divided by 2 times 100%, 85% yield. So if you've got this question down, you know how to find a theoretical yield, and you can figure out the percent yield if you're given the actual yield, of course. Cool. Burning sulfur in an atmosphere of fluorine produces the very stable compound SF6. SF6 is actually one of the worst, apparently, things for greenhouse gases, I guess. So SF6 is actually a controlled substance now, which is interesting, sulfur hexafluoride. Anyway, we wish to produce 2.50 moles of SF6. So what are we going to need here? How many moles of S8 and how many moles of F2 are we going to need? And from this information and that balanced equation, you can do it. You can use the stoichiometric factors to go from SF6 to F2 or whatever. See if you can do this on your own. Pause the video, and when you're ready, you can unpause it. So pause the video now. Okay, at this point, I'm going to assume that you've done the problem, and that's totally fine. So in this problem, we want a desired amount of product, SF6, and you want to calculate what the moles of the other pieces are. And to do this, we're going to use those stoichiometric factors like we used on the last time. So let me show you how you'd go from the SF6 to the F2. You would start with the 8 moles. Thanks for playing. So let me show you how to do this. You would start with the given amount, the product that you want, 2.50 moles SF6. And if you wanted to do fluorine, you would use 8 moles SF6 for every 24 moles of F2. And again, these aren't magical numbers here I'm using. They just come directly from the balanced equation, okay? So 2.50 times essentially 3 is going to be 7.50 moles of F2, all right? So I'm going to assume then that answer A is correct because that's the only one that's 7.50. Now, this number, 0.313, you should be able to get. You'd start with 2.50 moles of SF6. You'd still have 8 moles of SF6 on the bottom, but in the top, you would have 1 mole of S8. So 2.50 times 1/8, I believe, is 0.313. And if you do this, it does come out to be answer A. So in this problem, you use those stoichiometric factors once again to find the desired amount. So in theory, if you put 0.313 moles of S8 with 7.50 moles of F2, you would end up with 2.50 moles of SF6. Kind of a powerful technique. If you have a balanced equation, there's a lot of things you can do, and this is like one example of how that works. Ammonia is prepared by the reaction nitrogen plus 3 hydrogen makes 2 ammonia. And in this problem, we have 10 moles of nitrogen, and mixing them with 25 moles of hydrogen, the amount of NH3 produced will be, and there's 5 different answers. So see if you can use your understanding of the stoichiometric factors to figure out what's going on. Also note that because there are 2 reactant amounts, you've got moles of N2 and moles of H2. I would definitely be on the lookout for a limiting reactant problem here. If you see 2 mole amounts, those are almost always a limiting reactant problem. It doesn't say anything in this problem about limiting reactant, but I bet it is. So anyway, see if you can do this. This would be a good time to pause the video, work on the problem, and when you have the answer, you can unpause it. So pause the video now. At this point, I'm going to assume that you have done the problem and you want to see how you did on it, which is fantastic. In this problem, you're going to do the process we've used earlier. You're going to take the reactant amounts and figure out how many moles of product will be created. So as an example of that, you could start with 10 moles of N2, and there's 1 mole of N2 for every 2 moles NH3. So from the nitrogen, it looks like you'd have 10 times 2 over 1, 20 moles of NH3. But you really should do it for the other one too, all right? Because just because 25 looks like it's big compared to 10, but the stoichiometry sometimes will be really, really weird. So also do this from the other reactant's perspective. So you can start with 25 moles of H2, and there are 3 moles of H2 for every 2 moles NH3, and again the 2 and the 3 just come from the balanced equation. I'm going to take 25, multiply it by 2 over 3, and sure enough, I get 16.7 moles NH3. So we've got a problem here where the nitrogen says we can make 20 moles of NH3, but the hydrogen claims we can only make 16.7. And if your boss says, hey, how much ammonia NH3 can we make here? Well, you'd better give him the right amount. And the answer will be the smaller number. So what this says is that the amount of NH3 that's made, not 20, all right? The hydrogen, the H2, can only produce 16.7 moles of NH3. And this is an example of a limiting reactant problem. If you see 2 reactant amounts, all right, like here it was N2 and H2, you really should test both of them to see how much product can be made. And that's what we did right here. If you quoted your boss a 20 mole NH3 yield, you probably should be fired because you didn't check the other reactant. Bad call. In this problem, we would call the hydrogen hydrogen, H2, the limiting reactant. It's limiting how much product, NH3, that can be made. And because it's the limiting reactant, that means that 16.7 moles is the theoretical yield of NH3. That's how much we should be able to make. And then finally, by default, because nitrogen is not the limiting reactant, it's going to be one of the excess reactants. There will be nitrogen left over at the end of this reaction. So if you can do this kind of problem, you totally have this process down. A compound has carbon, hydrogen, and oxygen. And through combustion analysis of a 0.255 gram sample, we find that it gets 0.561 grams CO2 and 0.306 grams H2O. And we also find that there's a molar mass of 60.1 grams per mole. And the question is, what is the molecular formula? So this is the kind of problem we did in Chapter 4, Part 1. This compound has carbon, hydrogen, and oxygen in it. And you can at least relate the carbon dioxide back to the carbon and the water back to the hydrogen, but the oxygen can be a little tricky here. So anyway, I definitely encourage you at this point to pause the video and work on it. Just do as far as you can, and then we will answer this one. This is an important skill. This is a little bit more challenging one from Chapter 4, Part 1. So anyway, at this point, definitely start working on it. Pause your video now. Okay, at this point, I'm going to assume that you've tried the problem on your own and you want to see how you've done, and that's fantastic. These problems are a little bit challenging, but there's totally things you can do, and that's really important. There's a lot of compounds in organic chemistry that have carbon, hydrogen, and oxygen in them. If the compound only has carbon and hydrogen, these are pretty chill because you can relate the CO2 back to the carbon, you can relate the water back to the hydrogen, and find the moles of C and H from there. But with oxygen, we have to go through some kind of different kind of processes. I'm going to show you the math here in a second, but here's kind of the game plan. You want to first take grams of CO2, turn them into moles of CO2, and from moles of CO2, it's 1-to-1 with carbon. So you can find moles of carbon that way. That's like step one. When you have moles of carbon, you want to multiply moles of carbon by 12 grams per mole to get the grams of carbon, because all of the carbon in CO2 came from the CHO compound. So you're going to end up with moles of carbon and grams of carbon from the CO2. And you're going to do a similar thing with the water. You're going to take grams of water, turn it into moles of water. There are 2 hydrogens per water, but you can use that stoichiometry to find moles of hydrogen, and that's important. And just like with carbon, you're going to turn moles of hydrogen into grams of hydrogen. If you multiply by 1.008 grams per mole, that'll give you the grams of hydrogen. So at this point then, you've got moles of C and moles of H, which we'll use here in a little bit. But you also have grams of C and grams of H. And excuse me, those are important because this sample had a total mass of 0.255 grams, and that represents all of the carbon, all of the hydrogen, and all of the oxygen. Finding the oxygen is tricky in this problem because oxygen is part of the unknown sample. It's used to burn the sample, and oxygen is part of CO2 and water. But if you take that 0.255 grams and subtract the grams of C and grams of H, you'll have grams of oxygen in the sample by itself, which is really cool. And from there, you can turn grams of oxygen into moles of oxygen. You can compare the 3 moles of CH and O together to find the empirical formula. And then once you have the empirical formula, you can find the molar mass of the empirical formula, compare it to the molar mass of the whole thing. You're always going to get a whole number if the smaller number is on the bottom and the bigger number is on the top, and you can see which one of those it is. So let's look at how all this math works out. Oh goodness. Okay, let's break this down. First part here, we're starting with grams of CO2, turning it into moles of CO2, 44 grams per mole, and then 1 mole of C is 1 mole of CO2, so that's 0.0128 moles of carbon. Now from there, we can take the moles moles of carbon and turn it into grams of carbon. So that's 0.153 grams of carbon. And that's going to be important for us when we take it out of the sample. Now, the next part down here is the same process, but for water. Grams of water to moles of water. Here's the 2-to-1 ratio that happens. Water is H2O, 2 hydrogens per water. This is the moles of hydrogen. And then like we did with carbon, we're going to turn moles of hydrogen into grams of hydrogen using the molar mass. Now, the grams of C and the grams of H, we're going to subtract from the sample mass. 0.255 is all the sample you have. So if you subtract the carbon and the hydrogen from a sample which has only carbon, hydrogen, and oxygen, the remainder will be grams of oxygen, that number right there. And that's important because that grams of oxygen comes just from the sample. So grams of oxygen, we'll turn them back into moles of oxygen, this number right here. Now we have moles of C, moles of H, and moles of O in the compound. So this part right here is just finding the empirical formula. We divide all of the numbers by the smallest mole number, all right? And you can see that the oxygen, 0.0043 moles, that's the smallest one. The ratio comes out to be almost exactly 3-to-8-to-1. So the empirical formula, C3H8O. Now, to really do this problem right, let's find the empirical formula's molar mass. And if you take 3 carbons plus 8 hydrogens plus an oxygen, that's how you're going to find that number. So 3 times about 12 for carbon, plus 8 times about 1 for hydrogen, plus 1 times about 16 for oxygen. That comes out to be 60.095, that number right there. And you can see that's almost exactly equal to the 60.1 molar mass of the whole thing. So in this problem, the empirical formula and the molecular formula are the same. The answer here is E. Score. This process, like I said, is not hard. It's a little tedious, all right, I won't deny that, but it isn't too hard. So you can go through and stuff and figure that out. Now, one trick I have to offer you is, let's say you have a problem like this and you're totally blanking, all right? One way you can sometimes solve these is you can go through and find the molar mass of your 5 answers. All right, and C3H8O obviously is about 60.1. I can tell that answer B and D will have molar masses much larger than 60.1. So oxygen is 16. 16 times 3 is 48. And 48 plus another roughly 48 from the carbon is going to be more than 60.1. So it can't be answer B. The grams per mole is larger than the grams per mole that's given. And I'm pretty sure that D is out too. C and A, you'd want to double check and stuff to see. The ultimate way is to do it like I did it in this problem. But, you know, all my tricks are yours, all right? So this is one way that sometimes will help you to get through these problems. Which of the following is the only insoluble salt in water? So this is a question now about solubility, and it makes you think about the solubility table we started talking about in the Chapter 4, Part 2 lecture. See if you can figure out which of these is the only insoluble salt in water. And when you're ready, you can unpause the video. So pause your video now. Okay, I'm assuming you've worked on it, you're ready to talk about it, so let's do it. Knowing the solubility table is something that will help us a lot in the next several sections, and also into Chem 222 and Chem 223. If you aren't a person that likes memorizing tables, and I totally understand, there are some kind of quick ways to get around these. There are some ions, if you look at that table, which are always soluble, always AQ. One One of them is nitrate. Another one is sodium, like all the alkali metals. Potassium is another one. Lithium is another one. So you can see right away, I've underlined 4 of them. Wonder which one the answer is. But anyway, let me keep babbling here a little bit. Now, chloride, bromide, and iodide are usually AQ. So most of the time it's okay to say they're AQ, but they're not soluble when they're with silver, mercury, or, you guessed it, lead. So for all of those reasons, the nitrate makes that one water soluble. The sodium makes that one water soluble. Potassium makes that one soluble. Lithium makes that one soluble. And if you know the chloride, bromide, iodide exceptions, you can definitely say that, yeah, that's going to be soluble. So this one definitely answers C. Is going to be the one that's not soluble. We're going to run into the chloride, bromide, iodide, usually soluble unless they're with silver, mercury, or lead exception quite a bit. So I keep kind of pushing that on you. These ones down here, always AQ. So you could have sodium blah, 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 and you don't know what the heck blah, blah, blah is. You've never heard of it. Well, don't worry about it. The sodium makes that water soluble. So you would write AQ next to all the water soluble ones. But when it comes to PbI2 in water, you would put an S next to it. It is insoluble. It forms a solid. Which of the compounds below is not an acid in aqueous solution? An acid is something that gives up an H+, all right? And one of those down there is not an acid in water. See if you can figure it out, and when you know, you can unpause the video and we'll talk about it. So pause the video now. Okay, at this point, I'm going to assume that you've tried the problem and you want to see how you did. Most of the time in chemistry, acids will have an H listed first. And you can see that B, D, and E have H's listed first. Now, overall in chemistry, H's are not listed first. They're usually after carbon or something like that. So if the H is listed first, you know that's going to be an acid. B is phosphoric acid. D is hydrochloric acid. E is perchloric acid. So those are definitely acids. But you can see here that A and C do not have an H listed first. So one of those must be an acid and the other one is not an acid. And if you watch the video when it talked about the acids, A is acetic acid. The acetate ion is CH3CO2 minus, and a lot of times it has an H plus on it to make acetic acid. And I don't know why acetic acid is usually written this way, but it is. I'm just going to let you know. So acetic acid is not an acid, which unfortunately is usually has a hydrogen listed first, and that's frustrating. C is ammonia, and ammonia has hydrogens, but ammonia is not an acid, it's a base. If ammonia reacts with a little water, as we talked about, it's going to make ammonium, NH4+, and hydroxide. And things that create hydroxide are bases. So ammonia is a base, it's a weak base, like acetic acid is a weak acid. Just recognize two things. Ammonia, I keep pushing ammonia on you, I know. Ammonia is a weak base, it's not an acid. And acetic acid, for whatever reason, a lot of times the acetic acid, hydrogen, not listed first. And I apologize, but I am just the messenger. I certainly did not make these rules. There's some equations listed here, and it says which equation below best represents the balanced net ionic equation for the reaction of magnesium carbonate with nitric acid. And there's all those different possibilities, or more information is needed. See if you can do this problem. This is a good place to pause the video, try out the problem, see how you do, and when you're ready, you can unpause the video and we'll talk about the answer. So pause your video now. Okay, I'm going to assume that you've tried the video and you're ready to rock and roll on it, so let's talk about it. So you've got to know a couple of things here. You have to know what the equations are, and you have to know what kind of reaction is going to happen. And if you look at answer A, All right, magnesium carbonate is MgCO3, and nitric acid is HNO3. And you can see here what's happening. This is an example of a double displacement or exchange reaction where the magnesium and the H's are trading places with each other. Now, magnesium with magnesium carbonate is positive 2, and if it's going to start dancing with negative 1 nitrate, it's going to be MgNO3 parentheses 2, magnesium nitrate. And H plus, when it dances with CO3, initially it makes what looks like carbonic acid, H2CO3. But H2CO3 is an unstable acid. It breaks down often to CO2 and water. This is an example of a gas-forming reaction, okay? So the equation on A shows all the pieces. Now, let's look at the states of matter. Carbonates are usually insoluble. The big negative polyatomic ions like carbonate, phosphate, things like that, usually insoluble unless it's with sodium, potassium, lithium, ammonium, stuff like that. Magnesium is not one of those, so that's going to be insoluble. But nitrates are always AQ. So you can see the HNO3 is AQ, MgNO3 is AQ, no problem. H2CO3, when it breaks down, makes CO2 gas and H2O liquid. Carbon dioxide is a gas. That's why this is a gas-forming reaction. So answer A is a balanced equation, molecular equation, if you will, for this reaction. It looks really great. But we're not looking for the balanced molecular equation. We're looking for the net ionic equation. And net ionic equation is just a reaction that kicks out the spectator ions. Now, there's several ways to do spectator ion analysis, but when you do this for a while, if you see a chemical species in an aqueous chemical on both reactant and product side, it's going to be the spectator. And if you look at the two aqueous pieces, HNO3 and MgNO3, well, sure enough, NO3 minus nitrate is in both of them. Nitrate is in HNO3, nitrate is in MgNO3. So what that means for us here is nitrate is a spectator ion, and your balanced net ionic reaction, you don't want to have any nitrate. You don't want to break up solids, liquids, and gases, all right? So don't break up the MgCO3. Don't break up the CO2 or the water. Don't touch the solids, liquids, and gases. The spectators will only be in the aqueous pieces. But sure enough, if you do look at B, the NO3s have been removed from HNO3, so you have 2H+, and the NO3s have been removed from magnesium nitrate, Mg2+. So answer B is the net ionic reaction here. This part right here, the first equation in the answer, that's what the equation, quote unquote, looks like when you do the balanced double displacement exchange. But H2CO3 is an unstable acid, and it quickly breaks down into CO2 and water. So be aware that one's weird. It's going to break down. And from there, that's the balanced molecular equation, or answer A. You can pull out the spectator, which is nitrate, to get the overall one. When you're doing gas-forming reactions, remember to look for H2CO3, and once in a while, you'll see NH4OH. That also breaks down to NH3 and H2O. That's a pretty sloppy N, sorry. NH3 is a gas, and H2O is a liquid. Let me rewrite that. Gosh, it's weird writing with this kind of pen thing here. So sorry, NH3 and H2O. So look out for NH4OH, and in this example, H2CO3. Which equation below best represents the balanced net ionic equation, so no spectators, for the reaction of potassium hydroxide and iron 2 chloride to give iron 2 hydroxide and potassium chloride? So in this problem, I'm basically giving you the names of all the compounds, and I want you to balance it, pull out the spectators, and give me the balanced net ionic reaction. Okay, so this would be a good place to pause, work on the problem, and when you're ready, you can unpause it, see how the answer goes. Stop your recording now. Okay, at this point, I'm going to assume you've worked on it, you're ready to check it out and stuff, and that's fantastic. All right, so we got to translate a lot of names into formulas. Potassium hydroxide, KOH. Hydroxide's OH -1, potassium's +1, KOH. Cool. Iron 2 chloride. Chloride's always -1. Iron 2 means iron +2. So you're going to need 2 -1 CLs to balance that Fe2 plus FeCl2. It gives iron 2 hydroxide, so iron +2 and OH- makes FeOH2, and potassium chloride, K plus Cl minus KCl. So those are the chemicals you need. Notice, of course, like you have 2 Cls on the left and initially only 1 on the right, so you need to have a big 2 in front of the KCl, and also to balance the hydroxides out, then you need a 2 in front of the KOH. States of matter. All right, anything with K, Na, NO3, etc. will be aqueous. So KOH and KCl, definitely aqueous. Chloride, bromide, and iodide, usually AQ, unless they're with silver, mercury, lead, and irons, or potassium for that matter, not any of them. So that's AQ as well. But FeOH2. Now, hydroxide is another one of these big negative polyatomic ions, and usually those are insoluble unless they're with sodium, potassium, whatever. Iron is not one of those, so FeOH2 should be a solid. So answer A is the balanced molecular equation for this reaction, and that's totally cool. Now, to pull the spectators out, you want to look at the aqueous pieces, and anything that's in an aqueous piece on both the reactant and the product side is going to be a spectator. So KCl on the product side will be a good place to tackle this. So K is aqueous in an aqueous compound on the product side, and K is on an aqueous compound on the reactant side. So K plus is a spectator. Cl minus is in this aqueous compound on the product side, and it's also in Cl as FeCl2, another aqueous compound on the product side. So both K plus and Cl minus here are spectators. You don't want to pull out the iron or the hydroxide though, because they form the FeOH2, the precipitate, if you will, in this reaction. So in this reaction, if you pull out the spectators, answer C should be the right answer, which is 2 hydroxides and Fe2 plus making FeOH2 solid. And again, this is the balanced molecular equation, which shows all states of matter. Pulling out the spectators, and there's 2 of them here, chloride and potassium, gives you the overall net equation. Again, never break up solids, liquids, and gases, so don't break up the FeOH2. Good to go. Which of the following statements is correct regarding the reaction of zinc plus VO2 plus 1? And you've got 5 different possibilities here. And notice there's a lot of terms: oxidized, reducing agent, reduced oxidizing agent, etc., etc. And there's even a possibility that it isn't a redox reaction. So why don't you go ahead and give this problem a shot, and you can pause the video, and when you're ready, you can unpause the video and see how you did. So pause the video now. Okay, at this point, I'm assuming that you've tried the problem and you want to see how you did, which is fantastic. This problem obviously is about redox chemistry or oxidation-reduction chemistry. And you've got to know what reduced, oxidized, reducing agent, oxidizing agent means. My preferred way of doing this is through Leo, the lion says GR. Leo stands for lose electrons oxidized. GR stands for gain electrons reduced. And there's several ways to do this problem. But what I would probably do is I would go through and find oxidation numbers of the different species. So let's do that real fast for this reaction. So zinc metal is zinc with all of its protons and electrons. It's elemental zinc. That's going to be zinc 0. All right, so that's not going to, just has an oxidation number of 0. Most of the time, the ions, the charge is their oxidation number. So that's a +1 right there. And the next one's a little bit tricky. Vanadium is all over the place, but oxygen almost always -2, like we talked about. So we have 2 -2 oxygens plus some unknown vanadium equals +1. So it's like, let me write that out. 2 -2 from the oxygen plus X for the vanadium equals +1. So if you solve for what this is, the X here is going to be the charge on the vanadium, and that comes out to be +5. Pretty sloppy. Sorry, +5. So the oxygen, -2, vanadium, +5. Wow, I cannot write +5 for some reason. Anyway, whatever. That vanadium is +5. Okay, keep going. Zinc on the right-hand side, product side, has a +2 charge, so that's going to be +2 zinc. The vanadium over here has changed now, but oxygen is still -2. So for the VO2 plus, we would say X for the vanadium plus -2 for the oxygen equals +2. So if you add 2 to both sides, you can see that this vanadium, +4. Oxygen, still -2. And then on water, hydrogen's almost always +1, oxygen's almost always -2. Now, using these oxidation numbers, you can see something interesting. Zinc has changed its oxidation number. It went from a 0 to a +2, all right? And the only way it can go from 0 to +2 is if it lost electrons. So the zinc here has been oxidized, all right? Zinc has lost electrons, goes from 0 to +2. It's also become more positive if that works for you. But zinc is the part here that's being oxidized. It is not reduced, so we can pull B and D out right away. Zinc is that. Also, because zinc has been oxidized, that shows that yes, this is a redox reaction. Something else apparently has been reduced and stuff in here, but because at one part's been oxidized, yeah, this is a redox reaction. Now, going back to the oxidation numbers, hydrogen is +1 on both sides. So hydrogen is not participating in the redox chemistry. And oxygen is -2 all the way throughout, which it usually is. So oxygen here isn't doing anything. But the vanadium, and let me write this up here because this is so sloppy. Vanadium went from a +5 in the VO2 +1 on the reactant side to a vanadium +4. That was the oxidation number of the VO2 plus. And so vanadium has also changed its oxidation number. Now, if zinc has been oxidized, you must have something being reduced. So we're going to hope that this vanadium is going to be a reduction, and we'll see. And if you figure it out, vanadium is becoming less positive, or vanadium +5 is gaining an electron to become vanadium +4. So vanadium +5 here is being reduced. Zinc has been oxidized and vanadium here has been reduced. So it might be tempting to go down and say, oh yeah, okay, well here's reducing. That's the same thing, right? And no. Reducing agent and oxidizing agent terms show up a lot in this kind of stuff. And again, I'm just the messenger. I didn't make these lame rules, but a reducing agent is something that has been oxidized. It's the opposite. If you see the agent, it's like the opposite. So reducing agent basically says that VO2 plus has been oxidized. And that's not the case, because we saw right here that vanadium is gaining electrons, it's being reduced. Something that's reduced is also known as an oxidizing agent. So I would say in this problem, answer C is correct, and that is the correct answer here. So using oxidation numbers, we saw that zinc went to zinc 2 plus, that's been oxidized, or zinc is the reducing agent, that's okay too. We also saw that V and VO2 plus gained an electron to make VO2 plus on the product side. That shows that the vanadium is being reduced. We would call the VO2 plus one, we would call that the oxidizing agent. So knowing the terms is important. If you have one piece reduced, you have to have one piece oxidized. You can't have one or the other at this kind of level anyway. So be on the lookout for it, and definitely look out for those nasty agent terms. I don't like them, but again, I'm just the messenger, so alas. Let's say that we dissolve 6.73 grams of sodium carbonate in enough water to make 250 milliliters of solution, and the molar mass of sodium carbonate 106 grams per mole. What is the concentration of the sodium carbonate? Now, concentration in chemistry usually means molarity, moles per liter, so I'm just letting you know that. See if you can figure out the concentration of the sodium carbonate in this example. This would be a good place to pause the video. You can work on it, and then when you're ready, unpause it, and we'll talk about the answer. So pause your video now. Okay, I'm going to assume that you tried the problem and you want to see how you did, which is fantastic. So concentration is equal to molarity almost always in chemistry. We will see some other concentration units in Chem 222, but most of the time concentration and molarity go hand in hand. Molarity, the big M in those answers, stands for moles over liters. So in this problem, you want moles of sodium carbonate in the top, and you want liters in the bottom. Now, you've got to know how many milliliters are in a liter. How many milliliters are in a liter? If you said 1,000, you did a good job. Please know there's 1,000 milliliters per liter. We're going to use that a lot. So in this problem, you want to go 250 divided by 1,000. 0.250 liters is going to be the bottom, the volume term. The top part, the moles, you want to take 6.73 grams and divide it by 106 grams per mole. That'll turn your grams in per mole. So moles on the top, volume in liters in the bottom. This comes out to be 0.254 molar. That's the concentration of this solution. And you can see what I did down here, 6.73 grams divided by the molar mass. There we go. Divided by then again the volume in liters, 0.250 liters, and you have the concentration of the sodium carbonate, 0.254 moles per liter. 60 milliliters of 0.25 molar HCl are added to a 500 milliliter volumetric flask, and water is added to the mark. And it says, what's the concentration of HCl in the diluted solution? So this is an example where we're taking a concentrated solution, 0.25 moles per liter, and we're essentially adding a lot of water to it. So it's going to be diluted, which means the final answer will be smaller than 0.25 moles per liter. I would use on this problem M1V1 equals M2V2. So see if you can use that little hint and your knowledge of this section to figure it out. This would be a good place to pause the video, and when you're ready to hear the answer, you can unpause it. We'll talk about it. Pause your video now. Okay, I'm assuming you tried the problem and you want to talk about it, so let's get into it. So again, this is a problem where you have a concentrated HCl, you're adding a lot of water to it, so the final concentration will be less than you started with. So the answer will be a number less than 0.25. The moles of HCl here have not changed, and that's important. So for a problem like this, what I would do, M1V1 equals M2V2. You can also use MIVI equals MFVF, or C1V1 equals C2V2. They all mean the same thing. But the idea is here is you have an initial molarity and initial volume, and then you're basically adding enough water to make this the new volume. What's the new concentration? So in the M1V1 equals M2V2, you essentially want to solve for M2. M2 equals M1V1 divided by V2. So what I would do on this problem is I would go 0.25 times 60, that's M1 times V1, and I would divide by 500. You do not have to change to liters liters here unless you want to. There's nothing wrong with it, but lazy chemists like me will prefer to just keep it in milliliters. And because it's V1 over V2, a ratio, as long as they're the same kind of volume units, you're good to go here. So in this problem, here you go, you can see M1V1 equals M2V2. I solve for M2. It came out to be answer C, 0.030 moles per liter. And again, I did not change milliliters to liters. If you're using this process, you don't have to. There's nothing wrong with doing it, but I would, again, kind of keep it there. If you ended up somehow with an answer which was larger than 0.25, then something was wrong in the calculation. These diluted things should be less than what you started with. What is the pH of dilute nitric acid with a concentration of 0.030 moles per liter? And here are 5 possible answers. So see if you can use your knowledge of pH to figure out the answer. This would be a good place to pause the video, work on the problem, and when you're ready, just unpause it. We'll talk about the answer. Pause your video now. Okay, I'm going to assume you've tried the problem and you want to see how this all works out. No problem. This is a question about how to calculate pH. pH equals minus log of the H plus. And that thing in brackets there is a molarity. And for strong acids like nitric acid, that's the number that goes right inside there. Now, in this problem, you will need a base 10 log, log. You cannot use the natural log, ln, for these problems. It's a whole different kind of thing. But in your calculator, make sure you know how to do this, minus base 10 log H plus. So you go minus log 0.030, and if you did that right, you get answer B, 1.52. The pH should be acidic, should be less than 7 because it's an acid. If we were doing the pH of a base, it would be greater than 7. But honestly, these things are usually pretty chill. Good. What mass of sodium carbonate with a molar mass, 106.0 grams per mole, is required for complete reaction with 25 milliliters of 0.155 molar HNO3? So in this reaction, sodium carbonate is reacting with nitric acid, and this is a double displacement exchange reaction. So the sodium and the hydrogen are trading places. You end up with sodium nitrate, and you end up with what looks like H2CO3, which we talked earlier breaks down to CO2 and water. And in this question, we basically want to neutralize the 25 milliliters of 0.155 molar HNO3. We want to add enough sodium carbonate to make that happen. So using the balanced equation and your knowledge of how moles to mole ratios work, see if you can figure out which of those answers is the right answer. This would be a good place to pause your video and work on it. And when you're ready, you can unpause it. Pause your video now. Okay, at this point, I'm going to assume you've tried the problem. You want to see how you did, so very, very cool. Remember that big M, the 0.155 big M, that means moles per liter. And so if you wanted to find moles of HNO3, you could take 0.155 moles per liter and multiply it by 25 milliliters as liters. So remember, there's 1,000 milliliters per liter, so 0.155 times 0.02500 liters would be the way to find the moles of HNO3. You do have to use liters in this one. Big M is moles per liter, so turn 25 milliliters into liters first. Now, once you have moles HNO3, the balanced equation down here says 2 moles HNO3 per 1 mole Na2CO3. So the moles of HNO3, you basically want to divide by 2 to get the moles of Na2CO3, or you could multiply by 1/2. That would be fine. That'll allow you to find the moles of sodium carbonate needed to react with the HNO3. And from that number, moles of Na2CO3, you can use the molar mass, multiply, to get the grams of sodium carbonate. So if you've done all this, then here's the process itself. I turned the milliliters into liters, multiplied by the molarity of the HNO3. Here's the 1:2 ratio we talked about, and again, that came straight from the balanced equation right there, no magic. And then we multiplied by the the molar mass of the compound and of the Na2CO3, and of course that came out to be answer C. So if we put 0.205 grams of sodium carbonate in with that much nitric acid, we should have neutralized all of it. You'll end up with CO2 water and sodium nitrate. Good to go. A piece of copper, 5 grams of copper specifically, is heated for 2 seconds and 100 joules of heat energy is transferred to the copper. The temperature of the copper goes from 20 degrees to 71.9 degrees Celsius. We can use this information to calculate the specific heat capacity of the copper. So this problem is going to be one where you're going to use Q equals mc delta T. And the goal is to find the C of that equation. C is the specific heat capacity. Specific heat capacity is always a positive number. Answer E would not work here. I'm going to let you know that right now. I'm putting it in there just to talk about it. Negative heat capacities don't fly in thermochemistry. So the number will be A through D. Again, Q equals mc delta T. Solve for C. See if you can figure out which one it is. So this would be a good place to pause the video, work on it, and when you're ready, you can unpause it. We'll talk about the answer. Pause the video now. Okay, at this point, I'm assuming that you have tried the problem and you want to see how you did on it, which is fantastic. So let's talk about it. This problem, Q equals mc delta T. And it's the C part that you want to solve for here. The Q is the heat, the joules, all right? So for Q, you'd put 100 joules in there. And the M term is literally mass in grams, so you would put 5.00. Now, delta T, final minus initial temperature. Initially, the copper was 20, and at the end, it was 71.9. So your delta T here would be 71.9 minus 20, or 51.9. So C will be Q divided by M and delta T. You would go 100 divided by 5 divided by 51.9. And if you did this, it comes out to be answer B. Right here, you can see the steps. C equals Q divided by M delta T. 100 joules for Q, 5 grams for mass. Here's the delta T, final minus negative. Good to go. Delta T can be in Celsius or Kelvin. Notice the units of heat capacity are in Kelvin, but I use Celsius. A delta T, change in temperature in Celsius, is going to be the same as a delta T in Kelvin. So you can use either one. And in this problem, since I gave you Celsius temperatures, it makes sense to find it in Celsius. But again, there's nothing wrong with converting to Kelvin and then doing delta temperature in Kelvin, but I promise you're going to get the same 51.9 number. When 108 grams of water at 22.5 degrees Celsius are mixed with 65.1 grams of water at an unknown temperature, the final temperature of the mixture, 47.9 Celsius. What was the initial temperature of the other sample of water? Okay, so in this problem, we have a cold system, 22.5, and we have water at an unknown temperature. But the reason I said it was cold, the final temperature, 47.9 degrees. So notice that the cold 22.5 went up to 47.9. On these kind of problems, remember it's all about hot plus cold, making something that's in between, or warm, I guess would be the best way. So 22.5 is the cold, and we know that because the ending temperature was warmer, all right, 47.9. That also means that the other water system had to be at a temperature greater than 47.9. It was hot. Hot goes down to warm. Cold goes up to warm. We've got the cold going up to warm. We just need to know what the hot is. So the goal here is to find the initial temperature of the other sample of water. Now, in thermodynamics, the hot plus the cold, and that's supposed to be as Q hot plus Q cold, equals 0. And that's a way that scientists say that no energy has been created or destroyed. Now, each the hot Q cold and the Q hot, they're both going to be an MC delta T, all right? C is the heat capacity of water, and I hope you know that number or can look it up quickly. I'm not going to tell you until I answer it. Fascist chemist. Anyway, the cold has a mass of 108 grams. The hot has a mass of 65.1 grams. And delta T for the hot is going to be final, 47.9, minus the initial hot temperature, Ti. And that's what you want to solve for. Of the delta T here, you'll have TF minus Ti. You want to solve for Ti. You've already got TF, but you don't have Ti. So see if you can use this information to find the answer. Some of the answers do not make sense based on the thing we just talked about. So see what you can do. This would be a good place to pause the video, and when you're ready, unpause it, and we'll talk about the answer, see how you did. Pause the video now. Okay, at this point, I'm assuming you've tried the problem and you want to check out your answer, which is fantastic. So Q cold plus Q hot equals 0. That's thermodynamics saying no heat can be created or destroyed. We know that we've got something cold, the 22.5 degree sample, and we've got something hot, and they're coming together to make something warm, 47.9. So our answer, final answer for the hot thing, the initial temperature of the hot, it's going to be larger than 47.9. 8.9 does not make any sense here because that would be colder even than 22.5 Celsius. That doesn't make any sense. Also, it doesn't say anything about boiling water or boiling gaseous steam, and water boils at 100 Celsius. So 274 Celsius also doesn't make any sense. At 274 Celsius, we would expect our water to be a gas, not a liquid. And so that also would not, we'd have to have a phase change. We'd have to have mass times the heat of vaporization to figure out how that all works out. So the answer is going to be B, C, or D. And what you want to do is have MC delta T for hot plus MC delta T for cold equals 0. And there's different ways to write that. It's no big deal. Now, the heat capacity for liquid water is a number I want you to know. And that number, which is C here, 4.184. So the 4.184 will be the heat capacity for both hot and cold. All right. So on this problem, what I did is instead of writing Q hot plus Q cold equals 0, I put Q cold on the other side, Q hot equals negative Q cold. And each of those is its own MC delta T, all right? So you can see here for the hot side, here's the mass of the hot water, heat capacity, delta T, final minus initial. And it's that Ti that we want to solve for, by the way. And that equals negative Q cold, negative mass of the cold, heat capacity of the cold, and delta T 47.9 minus 22.5. Now, 4.184 actually cancels in this one. So if you didn't know 4.184, oh, you're lucky. No, seriously, we're going to use 4.184 a lot, so make sure you know it, but really you don't have to use it here, okay? And you basically just want to solve for Ti. Now, the whole right-hand side is just going to be a number, all right? And the left-hand side, you can reduce down quite a bit, all right? Like 65.1 times 47.9 is some number. And then that also times Ti is what you want to do here. So when you go through the math, and I encourage you to follow it, looks like the initial temperature, 90 degrees Celsius, all right? So the water started at 90 degrees Celsius. It was mixed with water at 22.5 Celsius, and at the end, it ended up at 47.9 degrees Celsius. Kind of a cool way to figure these things out. Propane, which is used in a lot of barbecues and stuff, propane has a standard molar enthalpy of combustion, negative 2,044 kilojoules. So what that means is that if you burn, which is what that reaction is, it's a combustion reaction, if you burn 1 mole of propane, you're going to get negative 2,044 kilojoules out. And this question says, what's the standard enthalpy change for the combustion of 3 moles of propane? So instead of 1 mole of propane, you want to burn 3 moles of propane. See if you can figure out which of those answers is correct. This would be a good place to pause the video. When you're ready, you can unpause it. We'll talk about it. Pause the video now. Okay, I'm going to assume that you've tried the problem and you want to talk about it, which is totally cool. This is a combustion reaction. Something organic plus O2 makes CO2 and water. And for every mole of C3H8 that's burned, negative 2044 kilojoules come out. Notice here what you could do. You could write negative 2044 kilojoules per 1 mole C3H8. This is a way that I kind of prefer. It says that you get this much energy out for burning 1 mole of C3H8. And in the problem here, we have 3 moles of propane. So I'm going to write 3.000 moles C3H8. So in this problem, you basically want to take the negative 2044 and multiply it by 3. Then the moles of the propane will cancel out. You'll have just kilojoules left over. The answer comes out to be A, negative 6,132 kilojoules. This reaction was exothermic to begin with. The enthalpy was negative, so the answer had better be negative as well. That's important. You wouldn't want to use the positive version. So the negative 2044 times 3 would give you the answer. Lots of energy released upon burning propane. This is a reaction where we're taking silane, SiH4, reacting it with oxygen to make silicon dioxide and 2 waters. And it gives you some delta HF, some heats of formation values there. What I'd like you to do here is calculate the enthalpy for this reaction using those values. And for this kind of process, the enthalpy of the products minus the enthalpy of the reactants is what you want to do. And you can use these numbers here. Now, there are 4 reactants and products. I didn't give you the delta HF for one of them. See if you can remember why I didn't give delta HF for one of them. Anyway, this is a good place to pause the video, work on the problem, and when you're ready, you can unpause it. We'll talk about the answer. Pause your video now. Okay, at this point, I'm assuming you've tried the video and you want to see how you did, so let's get into it. On a problem like this, you want to have the sum, it's the delta H of the reaction. It equals the sum, that weird sigma thing, the delta H of the products minus the sum delta H of the reactants. And again, I can't draw on this thing, so it's so sloppy. I'm really sorry. But anyway, I hope you get the idea. Delta H of products minus delta H of reactants. All of these delta H of formations are enthalpies per mole. So the SiO2 we're going to use as is. We're just going to use that one. But because there's a 2 by the water, we're going to take this number and multiply it by 2. And that's going to be this part. That's the delta H of the products. Now you want to subtract, and remember always to subtract, the delta H of reactants. We're given the delta H for silane, so that goes over there. But notice there is no delta HF for oxygen. And the reason I didn't include it here was to make a point again that the heats of formation, the delta HF values, will always be 0 for the elements in their standard states. So any of the elements in their standard states are just going to be 0. So on this one, you don't have to worry about the O2s. They're just equal to 0. So to figure this out, you take products minus reactants. You take the SiO2, negative 910.9, plus 2 times negative 241.8, and those terms would be the delta H products. Then you subtract the only delta H of reactants that's needed, so minus 34.3. If you put that in your calculator, If you put that in your calculator, it comes out to be negative 1,428.8 kilojoules per mole. And again, you can see here, here's the delta H of products minus the delta H of reactants. The O2 was 0, so we don't have to worry about that. Make sure you do subtract the reactants. Once in a while, I'll forget that, which isn't a good thing. This is an exothermic reaction. These delta HF values are the ones from the table in problem set 5. And on an exam or something like that, I would give you the ones you need. I may not give you like oxygen, all right? You have to be hip about that. Sorry, fascist chemist instructor. But all stuff you can do. And honestly, if you don't have a value, it probably means it is 0 because your instructor is... Anyway. Which of the following equations below defines the standard molar enthalpy of formation for gaseous methanol, CH3OH? So this question is basically saying which one of these equations is a delta HF, all right? In the last problem, we used delta HFs to products minus reactants. And one of these three, not E, please care, all right? This hopefully is important somehow to your future and stuff like that. Methanol, if you do drink methanol, it does make you go blind. In the days of Prohibition, when people made illegal moonshine, a lot of times they would have their alcohol that they made in bathtubs or whatever, it would be contaminated with methanol. And if you drink the methanol with the ethanol, it'll make you go blind and stuff. So anyway, stupid answer. It's going to be A, B, D, C, or D. Anyway, see if you can figure out which of those it is. There's some specific rules for delta HF equations, and that's what I'm having you focus on this problem. So this would be a good place to pause it, think about it, see which one of those is the best answer, and when you're ready, you can unpause the video. We'll talk about the answer. Pause the video now. Okay, I'm going to assume that you gave the problem a shot and you want to see how your answer did, so let's get into it. If you are creating a delta HF equation, which is what this is, and delta HF is the standard molar enthalpy of formation, all right, then a couple of things. You can only have 1 mole of product, all right? And if you look at A, B, C, and D, all of these have just 1 mole. If you had, for example, like a 2 right there, then you wouldn't want to use that, all right? It has to be 1 mole of product. But the other thing that's important here is all reactants must be elements in their standard states. So if you look at answer A, oxygen, O2, that's an element. That's its standard state. Oxygen is normally a gas. It's what you're breathing right now while watching this. It's not oxygen is a liquid. It's not ozone, something like that. That's oxygen's natural state. But CH4 is a compound, all right? It's a mixture of carbon and hydrogen. And in a delta HF, you can only have elements in their standard states. So A is not going to work because CH4 is a compound. And if you go down like C has CO, that's a compound, that's not going to fly. Water is a compound, that's not going to fly. So answer B here is the best answer. In this compound, in this equation, we have 1 mole of product, and the reactants are elements in their standard states. So carbon, hydrogen, oxygen are standard. H2 and O2 because they're diatomic. The carbon would be graphite, although it doesn't state that, but that's the cheap version, basically carbon, more common. So answer B here is the heat of formation equation for methanol. And again, important parts, 1 mole of product, and all reactants are elements in their standard states. In this equation, I'd like you to calculate the standard molar enthalpy of formation for FeCl2 using the following. And we have here 2 equations, both involving FeCl3. Now, be careful here. We're looking for FeCl2, not FeCl3. This is an example of Hess's law, and I want you to figure out essentially the heat of formation for FeCl2 using Hess's law and these 2 equations. This is going to be a good place to pause your video. You can work on this, think about it a little bit, and when you're ready, you can unpause it. We'll talk about the answer, so pause your video now. Okay, at this point, I'm assuming that you've tried the problem and you want to check out how you did. So let's, without further ado, let's get into it. Let's write out what the standard molar enthalpy of formation for FeCl2 would look like. And this is kind of like what we did in the last problem. But remember that standard molar enthalpy formations, 1 mole of product, so FeCl2, and all reactants elements in their standard states, well, that's going to be Fe and Cl2. Those are the standard states for iron and chlorine. So this is the desired equation, and we want to make these two equations look like the last one, all right? And you can see that right now that's a little confusing. What I look for on these kind of problems is, for example, like we want iron as a reactant, and iron is a reactant right here. So probably then we can use this equation as is, but you don't want FeCl3 as a product, you want FeCl2. And the top equation, or the first equation right there, it has FeCl2, but it's a reactant. We want to have FeCl2 as a product. So I know right away then on that equation, we're going to have to flip it around. We're going to make the 1/2 Cl2 and FeCl2 as products, and FeCl3 will become a reactant. And when you do this, the delta H value becomes positive. You change the sign of it. It becomes positive 57.7 kilojoules. When you flip an equation, you change the sign around. So on this equation, on this problem, that's what I would do. And if you do that, you can see that's exactly what happens. I want iron as a reactant, so I'm going to leave that equation alone. But the other equation, I want to flip because I want FeCl2 as a product, not a reactant. And in the meantime, when you flip it, you can see what happens. The FeCl3 that's a product here will cancel the FeCl3 that's a reactant there when you add these equations together. And also you have 3/2 Cl2 and 1/2 Cl2. Subtracting 1/2 Cl2 from both sides makes that one go away, and you have just 1 Cl2. So the Fe plus Cl2 goes to FeCl2. And remember to change the sign of the delta H, but then negative 399.5 plus 57.7, delta H negative 341.8 kilojoules per mole, answer B. So this is an example of Hess's law, how it can be really handy for things. Pretty cool. Okay, so that's the end of this review session. I really appreciate you spending your time with me and going through these problems. If you need more assistance before the midterm, which I totally encourage you, there are practice problem sets online. I do encourage you to check them out. The concept guides for each of these sections will also be helpful, and those are both in the companion and online. Chapter guides are basically bulleted lists of things where you can look over the concepts. There's end of chapter problems in the textbook. Every other question has the answer at the end, and that's what I've done a lot of times when I'm studying for things. There's also some sample exams online. You can see what they're like, where they have the answers but not worked answers, another way to test yourself. Lots of ways for you to get assistance. And of course, you can reach out to me for help. I'm more than happy to help you through this. I know this stuff can be a little bit strange. Regardless, I do wish you the best with your studying, and have a wonderful day.